These are exciting times for C++. And one of the things that motivates me to say that, because believe it or not, I do not say that every year, is because this year, at our two standards meetings so far in May and in June, we have made great progress that didn't just happen during those 2 weeks, but that has been building for years. And now we're, you know what it's like to work on a project for a long time, and then you're getting close and it's becoming real. You go into beta, you start to ship it. That's where we are with some major features in C++, and it's just a joy to see it coming together. To me, we are at the beginning of a decade, and especially with what looks like the C++26 standard is going to be a treasure chest. I promise some of you are thinking, but could it be a mimic? No, it's a treasure chest of features that I think are likely to change the way that we develop software, to upgrade our C++ development and our code and our tools in a way we haven't seen since C++11. C++20 was great, I love the features in it, but C++11 was the most impactful release we've done in 20 years, with all of the features in that. Like, we didn't even have standard smart pointers before that, much less auto, range 4, and lambdas, and many more, move semantics. So what is in this treasure chest? There's lots, and I'm just gonna mention on this slide 4 features that appear to be on track, fingers crossed, to start being delivered in C++26, and I'll explain what I mean by start being delivered in a second. But I'm gonna focus on these 2 in the middle. Type and memory safety improvements, which are important for us to do, and we're starting to see real progress in the standard already in C++26. And reflection. I'll often say reflection, like reading the program state, and code generation, writing program state, creating more source code. When I say reflection shorthand, I mean both of them, but I'm trying to call out generation just so we don't forget about it. This talk is in 3 parts. The first part is about reflection, and I'm going to be focusing on what the state of the art is in the implementations of the proposal that was just 2 months ago, 3 months ago, design approved on the language side for inclusion in C++26. It's not voted into the draft yet, but hopefully that will happen in the next meeting or 2. Then we'll talk about safety, including improvements in progress there, including some already in C++26. And then we're going to come back to both of those in the sense of looking forward. How will each of these contribute to making our C++ code simpler, our C++ tools simpler? Normally, I don't include 2 different topics in the same talk. A talk should have 1 topic, 1 main theme. But these really are related, and the reason I'm doing that is the intersection of 1 and 2 is not just number 3, that's the 4th bullet, how it's going to simplify our code and our tools, but they have more things in common. They have timing in common. Both are starting to ship in C++26. And now, by the way, C++26, you might think it's 2024. He's talking about C++26. Call me again in a couple of years. We are only 9 months away from feature freeze on C++26. And compilers, GCC and Clang, have already implemented 2/3 of the features already approved for C++26. Go look it up on CPP reference. They have a great compiler conformance sheet. This is real stuff that's getting real quickly. Second, there's a technical overlap. We're going to talk about greatly reducing undefined behavior as something both of these 2 things have in common. And if you think reflection, really? Wait for it. And this week we have over a dozen talks on those 2 things. So let's start with reflection. The short definition, we've all heard of metaprogramming. We've been doing metaprogramming, usually with templates, so angle bracket syntax, abusing for fun and profit the C++ template type system as a functional programming language. Sort of accidentally existed in C++, and boy, do we use it. And we call that metaprogramming because the word meta tends to be overused, but when it's used correctly, as it is here, it's like a meta function is a function that manipulates functions. A metaprogram is a program that manipulates programs. It reads and writes actual code. That's what reflection is going to let us do. How many of you have used reflection in other languages like Java, C#, others? Leave your hands up if you find it very useful and like it. Okay, more hands aren't supposed to come up. Okay, we'll have a primer on set theory afterwards. So it's really useful, right? But what's the caveat? It's slow, right? Because it's runtime. It's not super slow, it's usable. But for instance, a function call in a virtual function call in Java, if you do it by reflecting on the type and then calling it, is about 3-4 times slower than a direct virtual function call, that kind of thing. This ain't that. This is purely compile time reflection. But don't worry, if you do want any of that information at runtime, just store it. But that way you don't pay for what you don't use. And that is our world in C++. And this reflection is part of a 30-year arc toward more and more compile time metaprogramming in C++. It is 30 years ago this year that Erwin Unruh came to the C++ Standards Committee and said, look at this wonderful program I wrote that doesn't compile. But it fails to compile. It fails in a very useful way, which is to print the prime numbers in part of the error messages. This didn't, you might think this would scare people. No, it made them say, I wonder what else I can do with this. And we've been doing that for 30 years. The TC means we just discovered we have a Turing-complete language in our template type system. What else could we do? Well, that was 1994. 7 years later, we got template metaprogramming on steroids with our friend Andrei Alexandrescu, who wrote the seminal book, Modern C++ Design, one of the most important C++ books ever written, still is, because it pushed the boundaries farther than anyone had and put it all in one place. In fact, he tested all the code. So 90% of the code in that book, I think roughly, you can correct me, Andre, compiled on some compiler, so he could test it. Not a single example, I don't think there is any compiler, rather, that could compile every example in the book. But we got there, so it really drove the industry forward. How many of you enjoyed reading that book? Lots of hands. We have Andre here in the front row. Could you just stand up for a second and take a bow? Thank you, Andre, for that. Now, this showed how far you could get with angle brackets, with abusing templates as a functional programming language. But this has been a stepwise improvement where we've been delivering a little and then a little more and then a little more for years. In C++ 11, we got const-expr functions. Bjarne Strustrup, Gabriel Drossreis, and Jens Maurer's names are on that paper, and many others helped. The whole standards committee helped. Brian B. from Bloomberg and others debug that kind of thing. Actually, I don't remember if Brian was in the committee then, but all the people who were there helped get this right. Now, it was tiny. You might be forgiven for thinking, oh, this is like a little curiosity. Seems like a one-off feature. Maybe it won't go anywhere. Because all you could do in a const-expr function is have a single return statement. But even that was powerful, because that started requiring us to build a C++ interpreter, basically, in a C++ compiler, because we had to execute this at compile time. Well, the experiment worked, because in C++ 14, we gave you if and switch, for and while, more statements, local variables. In C++ 17, lambdas, if const-expr. C++ 20, you can do dynamic memory allocation, dynamic exception handling, allocators, vector and string at compile time. This is giving us already a huge subset of the language. Most of our language is now in C++ 23, available at compile time, and that's good because we're going to use that to write reflection metaprograms. But it's not just const-expr. Oh, by the way, we have Ben Dean here, and Jason, please stand up. You gave a great talk in 2017 about const-expr, all the things. Here at this conference, and I just love that talk because it delightfully encapsulated what we saw happening. It's like, man, this was 7 years ago. We realized we're going all the way here. We're going to have basically all of C++ available at compile time. But it's not just const-expr where we've seen this progress. Those of you who've done GPU programming, do you remember the days back in when dinosaurs roamed the earth, where GPUs had something called shaders. And so the GPU model, especially then, was data just flies by. It was a data flow-driven memory model, so no cache at the time. But as that pixel flew by, you had a little instruction buffer where you could write, I don't know, half a dozen, I don't know how big they were, just a few instructions that you could throw at that car as it drove by. You could throw at that pixel as it went by. Turns out that you can make a lot of data look like a pixel just to abuse that to do computation. And then we got more. We got longer instruction streams. We got variable length instruction streams that could do loops, branches. Then we got lambdas in OpenCL, SYCL, but also CUDA I'll use as an example, as a preeminent example. Lambdas, range 4, static assert, again, new and delete sound familiar, and const_expr code sound familiar. Now let's compare those two staircases. Do they look similar? They do, and it's not by accident. Pause and think about what that means for a moment. So we want to do more metaprogramming. So what did we do? Did we invent another meta language within C++ to learn? No, we said we want to write C++ code, normal C++ code, but that runs at compile time. We wanted to run code on GPUs. Did we invent some other language? No, we figured out as an industry with lots of investment, how do we run more and more of C++ on GPUs? Now we're taking the same stepwise approach with reflection. So I do this partly to set your expectations. Most of the things in this talk are not things that you can go and use in production today, although I will mention a few things that you can because of compiler flags that exist today. But we are now on the cusp of starting to ship the first parts of this important feature. So I'll show you examples of where even in this initial proposal, P2996, there's already a lot of usefulness. But think of it as C++11 const_expr. And there's already more papers to add reflection on function parameters, on closure types. Then I added dotted line because then we cross into generation to actually generate new source code from the things we reflected. And I'm going to give you examples of all of these. Not everything will be in C++26. We hope the first one will be. But this is going to be like const_expr where this rolls out. And we're going to be spending the next decade learning how to do this, learning it, and then learning what possibilities it opens up, the code that we could never write before, or that was too hard to write to be practical. So here's one of the many examples. I refer you to P2996. It's got lots of examples. We don't have time to go through all of them, but here's one. And thanks to Matush, who presented this initially, I've got a struct that specifies command line options. But I actually specify them in the C++ type system, where each data member of the struct is a command line option. And at first you might think, oh yeah, well that looks normal. And then you start to realize, well wait. The names in the C++ source code in the static type system, but we're talking about runtime strings and parameter. Wait, how does this work? Like, how are these connected? But this code works today, and I'll show you on the next screen how, where you can just call parse options and pass it that struct, and the parse options function will not only take the struct like any regular template might, but it will take that, and the type itself is input. Just the structure of the type is itself input. So this is not like a regular template, because the first thing we're going to do is something you've never done in a template before, at least not in a standard C++ compiler. We write for each loops over vectors all the time. We're going to start writing for each loops over the data members declared in that struct to see their names, to see their types. And so we're going to go through and look at all the non-static data members of that reflection. We're going to grab the identifier. Then we're going to, as we go and look at the runtime parameters as well, we're going to see if some of the names match. If the name matches, then we'll try to say, okay, well, they asked for this name. We'll go get its type, and we're going to try it in perhaps a C++23 ISPAN stream is one way you can do it. We'll try to convert the string the user gave us and convert it to that type, that member name. Well, that member name I have to splice in because I don't know what it is at the time I'm writing this code, but I reflect and I get the member name that I matched. And if that works, if the string the user gave can be converted to that thing, great. Otherwise, we say, oh, that's not valid. And by the way, when we say that, oh, what you wrote is not a valid int, say, your first reaction might be, well, isn't this like typeid.name? No, because typeid.name is at runtime and it doesn't give you the exact type name. It might give you like I instead of int. This is purely compile time, and it gives you exactly the types and names that the user wrote. And so you can do this on Godbolt today, enter that example, and if at the runtime you put --count42, --file name Scott Meyer's Effective Modern C++, which is still a great book, go get it and read it, then you can see the program output that it successfully pulled that string and that int out of the command line. By reflecting on, you said, oh, you want these command line options, you just pass them as a struct, strongly typed, and it worked. And if you pass something that's incorrect, like a count of Scott Meyer's Effective Modern C++, I don't know, is that supposed to be pages? Well, that's not an integer. Sorry, count is not a valid int. So that word count and that word int was reflected at compile time, and then because we wanted to use it at runtime, we just saved it and then we printed it out at runtime. But this is purely compile time, purely don't pay for what you don't use. The implementations available today, there's two, EDG by David van der Voorde, that's the first picture, and a Clang-based one by Dan Katz at Bloomberg that Brett referred to in his introduction. And there's other related prototype implementations that also do forms of reflection for C++. I'm the author of one of them. But the first two are ones of specifically the proposal that has now been design approved just 3 months ago on the language side for inclusion in C++ 26. So hopefully in the next meeting or two, it could be, fingers crossed, part of C++ 26. And speaking of David, he's giving the final keynote for the conference on reflection. And I swear I had nothing to do with that title, Gazing Beyond Reflection. This one is peering forward and his is gazing beyond. Accident. We both kind of like looking or something. Andre is giving a talk on reflection on Wednesday, and there's a couple of other talks. So be sure if you're interested in this to watch these talks here this week. Now let's switch gears and talk about safety. So I wrote an article, there's a longer essay there with much more detail. I'm going to cover a few highlights here, but also show how it's related to what we've just been talking about. We want to improve memory safety in C++. I use this graphic just to emphasize, let's not forget that even though memory safety is important, we want to defend against that tank, that one attacker, we're not done once we do that. There's all sorts of other attacks, SQL injection and information disclosure, supply chain attacks, there's all sorts. We need to harden our software because it's under attack. But in our part of the world, narrowly, I'm going to look at how do we harden this part of it in the programming language we're responsible for, and what progress are we seeing? So just some terms. Software security, these are standard terms. There's a standard reference at the top. Software security means defending our assets. The program can't be made to divulge things about itself or its data. Software safety means the program doesn't do unintended harm. Both of those are helped by programming language safety, which includes type and memory safety. This helps both of the others. It also does more, which we'll talk about again. We'll come back to this slide in section 3. But when I say safety by itself, I usually mean programming language safety, but it's worth remembering that, because these terms often get cloudy and get muddled, we should use them crisply. They're software security, software safety. Programming language safety guarantees help both of those. So in a nutshell, here's the TLDR slide about safety. The actual thing we want to achieve is parity with other modern languages. Nobody needs perfection. There is no commercially widely used memory-safe language that is formally provable. Doesn't have to be. They are hardened and safe and de facto in practice and give very useful guarantees. But the biggest difference between C++ and especially C, and to a lesser extent C++, with the memory-safe modern languages is these 4 categories: type safety, especially bound safety, initialization safety, and lifetime safety. Bounds is the biggest one. And I say that because every time you look at the most severe vulnerability categories from MITRE, from CERT, every year, the ones that are attributable to programming languages, which last year was 7 of 25 were attributable to programming languages, so memory safety could help with those 7 out of 25 categories. It's always these 4 things: bounds, type, initialization, lifetime safety. And it's been this way for years and years. So this is where we want to fix the problems. This is where the actual vulnerabilities are. But this is also the 4 things that other languages do better than we do. So when you see people say, oh, well, C++ is too unsafe, you should go use other language, it's because of these 4 things. Like, these are the 4 things. So this is why we want to address them. There's progress already and even more progress coming. So we've already done a little bit. Even in C++20, we standardized std span, so we could use that instead of pointer arithmetic because the span knows its bounds. We still have one more step to do, which is to actually enforce those bounds. And we could do that as a part of a bound safety profile. We're also working on profiles, that's the 3rd point, which takes many rules we already know, and it does a shift left to run them at compile time in the compiler rather than as a separate tool you might or might not have. Those 12 rules, 24 rules that are very useful currently are spread across thousands of rules and linter-style rules that tools may enforce. We want to take those key ones about type and memory safety, move them to compile time so that they run before check-in. That's a super useful feature. We also want to get rid of safety-related undefined behavior. Notice we do not want to get rid of all undefined behavior because it's important for optimization. Not all undefined behavior is unsafe. But the UB that impacts safety we want to do something about, including by adding dynamic safety checks where we can't do it statically. And I'm going to talk a bit about what implementations already let us do, even outside the standards, such as F-hardened is coming along and STL safety. But I want to emphasize that we're not trying to turn C++ into something else. If you want to write Java or C#, we have Java and C#. They're great languages, go use them. If that's the right tool for the job, use the right tool for the job. If Rust is the right tool for the job because it's got thread safety guarantees that C# and Java don't have, do that. But we don't want to change C++ to be like something else. We want it to be a better C++. So the metaphor I use is, you're never going to take a sharp knife out of the hands of a C++ programmer because we want those knives. We need those knives because we're chefs. It's part of our job as the tools of our trade. But right now, especially in C and to a lesser extent in C++, those knives are scattered around the kitchen. They're all over the floor. You have to watch where you step. That's where foot guns come from, or foot slices, right? So our bunny rabbit here, our chef, has got a wrapped up foot. Because, why? Because it's too easy to hurt ourselves by accident. So I summarize this as performance and control by default. That's our bread and butter. Safety is always available. It is possible to write robust, safe code in C++. But if you make a mistake, often it will compile and run and you don't know it. That's what we need to fix. So today I call this the watch out model to make sure you're not running something unsafe. We would like to be in the same kitchen, using the same knives, all the same tools we have today, but in an opt-out, not a watch-out, but an opt-out model, where we have safety by default and performance and control always available. Nobody's going to take performance and control away from a C++ programmer. We wouldn't be C++ anymore if we did that. So what's the difference? Same knives, same kitchen, but let's put the knives in a drawer. Imagine, so that we opt into using it when we want to take that knife out of the drawer, that it's not just lying around to trip on. That's the direction that we're going. And that way we're still C++ and still get safety guarantees. So the safety profiles work that Bjarne and Gabby are pushing forward are helping to shift left some of these well-known safety rules, a couple of dozen of them, most of them well-known and a couple that we're going to add, and implement them at compile time. Each one, if your code compiles clean, will show it's absent of a class of defects, and we want to make it easy to opt in for a volume of code to make it the default in that volume of code. But now let's talk about undefined behavior. And I have to give a shout out to my friend Robert Secord. So I run the C++ Standards Committee. He currently runs the C Standards Committee, and he's also the author of Effective C. The second edition just came out, there it is. And from the praise page, you can already see that part of his mission is not just to document C, but also how to avoid undefined behavior. Robert is not just a C guy. He has been doing security work at CERT and at MITRE for decades. He's also the author of secure coding in C and C++. So when he teaches C, he's teaching best practices to avoid UB. Anybody recognize that character? Not the robot on his shoulder, but the main character on the front of the cover? Just shout it out. Oh, wow, everybody knows, okay. Anonymous no more. Lots of Lovecraft fans here, okay. A great old one, Cthulhu, cartoonized to be cuddly. Let's not think too hard about that. And I love, on this praise page, this last quote that I haven't shown you yet, I just love it because when I asked Robert about it, he said, yeah, the guy made a joke and it got past the editors and into the printed book. But what's he saying? Michal Zalewski is saying, we use C and C++. We use C because we want the ability to say what we mean, to open the hood and to use undefined behavior when we want it and when we can test it and do it intentionally. One little nit, other languages don't open portals to hell. Actually, I know one other language that does. But we're going to do something about that. So the reason that it's called portals to hell is because the usual examples of undefined behavior, if you have undefined behavior in your program, are you get demons flying out your nose, so nasal demons. Somebody invented that in I think it was the 70s, and it just got so popular that it took off. Maybe it was the 90s, I forget. It's been a hazy few decades there. Or to format your hard drive. But those things don't actually usually happen when you write undefined behavior. Serious things do still happen, though. Time travel optimizations, where you can't even reason about what your code did because it's not even the program you wrote that's running at that point. Leaking secrets, I'll give an example of that. And so here's something we did earlier this year in March of 2024. And we voted into draft C++26 that for the first time in 20, 30 years, directly it starts to address this problem of UB. So I'm not talking about some proposal that might make it through committee. I'm talking about something already voted in 6 months ago to draft C++26. That's one of the exciting things happening this year. We now have this idea, thanks to Thomas Koppe, of undefined or erroneous behavior. And I'm going to take a pretty much direct quote from the paper. And this is not a joke. It sounds like a joke, but it's not. It's well defined as being just wrong. Now think what that means. It means that it's still wrong, like you shouldn't do that, and the language happens to let you do that, but it's well defined. You cannot get time travel. You cannot get leaked secrets. You do not get undefined behavior. And the first place that we applied this general tool was to uninitialized local variables. In C++26, reading uninitialized local variables is no longer undefined behavior. It cannot format your hard drive, give you nasal demons, summon Cthulhu, or give you time travel or leak your secrets. And that is a huge, monumental improvement. Even if it just gives you a few % improvement in vulnerabilities, I'm going to show you why it's important. And that's just the first place that we're applying that. So when you write an uninitialized int and then read from it in C++26, if you compile that code with the C++26 compiler, it is required to overwrite the storage with an erroneous value. Let me show you how that works. But let me also, before I show you the code, think about why this is important quantitatively. It's going to help a lot of code because it changes the meaning of something, of code that already exists from something unsafe to diagnosable, and that doesn't give you UB. But also qualitatively, I'm really glad to see us doing this because we're delivering it in such a way that all I have to do is recompile existing code with a new compiler, and it's safer. I didn't have to do manual code changes. Have any of you ever tried to sell your boss or to sell another team about a great idea that would make a legit, really good improvement, and you say, you just have to update like 1 in 100 lines of code? And that's where you lost them, and you're not invited back to that lunch, right? That just creates a barrier. It is enormously valuable. It is enormously more valuable to say, just recompile your code with no manual code changes, and it'll be safer. And so we want to do more of that. So here's the example. Let's say we have two functions we call f1 and f2 in main. f1 has a local character array that contains a secret on the stack, and then it returns. Then we call function f2, which also declares a character array on the stack, but it is uninitialized. It could be a std array of char6 or something else. It could be a bunch of ints. If you print that today, likely you will see the word secret, even though that's a completely different function. Because it was uninitialized, we overlaid another piece of data over a deallocated storage and got to read what was in that storage because we didn't initialize it. In C++26, that will print something other than secret. Standard doesn't specify what, but this will be safe from information disclosure. And I'm not just making this up because you can do this today in GCC and Clang using -f trivial autovar init equals pattern. If some of you are saying, why not equals 0? There's a slide for that, hold on. And in MSVC, you can do /RTC1. And it will give you this behavior. And here you can see it in action on Godbolt. You can try this yourself. The three compilers in order from top to bottom are GCC, Clang, and MSVC, all the very latest trunk versions. And you can see the secret being disclosed. Until you flip those switches that I just mentioned, and then the secrets are not disclosed. So you could use those non-standard switches today. Run, don't walk, to start to consider using those. But in C++26, you won't need to use those switches anymore because that will be the default. This is an example of making C++ safer already in this standard that is only 9 months away from being feature frozen. Like we are deep into C++26 standardization. And this is real, this is shipping, this is going to ship. So why not zero initialization? Well, if we had a time machine and we could just say initialize stack variables, stack ints to 0, then we would know that all the code that did that actually meant the 0, right? But we didn't. If we now retroactively try to jam in zeros, we have no idea if that's sensible for the code, if the code actually will do anything useful with 0. Probably will, because 0 is a pretty commonly useful value, but it's definitely not always useful to the program. And it is known that something like 30% of the time, that will simply change one bug into another. But worse, it actually creates new problems. Because by jamming in 0, undefined behavior sanitizers that run later and look at the values and don't have the source code now can't tell. They can't tell that this isn't a real initialization. It's still a bug, but we've now hidden it from our UB sanitizers, depending on how the UB sanitizer works. So those are some reasons not to just jam in zeros everywhere, because that could change the meaning of the code in an unuseful way, change one bug into another, and actually mask bugs. Next question is, can I opt out? Yes, of course, this is still C++. The knife is in the drawer, but if you want to open the drawer and get the knife, you can say indeterminate, and you can opt, but you opt into the unsafe behavior. You say, hey, I know what I'm doing, and you can grep for that. So it's now explicit in your code that that's what you want to do. Why didn't we always do this? Performance reasons, especially for big structs and arrays on the stack. I'll come back to that in part 3. So I've just been making a case for raw C++. We're going to get rid of all undefined behavior that's safety related, all language undefined behavior that's safety related. How many of you believe that unconditionally right now? Ooh, a few hands. I was expecting a few more. I got to work on my being convincing. I'm not a very good cult leader. Okay, that's good because we're not that. So That's good. I will put on my job description. Not a good. But how many of you, with a bit of more data, could be convinced that, yeah, I think we can get rid of most safety-related language UB? Still only about 1/3. Wow. We already have. There are great gobs of C++ code out there, including code that many of you have written, that do not have language undefined behavior already. And this is the intersection I promised to talk about between compile time programming, it's like const eval, reflection generation, and more safety, because part of that, one of the things in that intersection is less undefined behavior. Now, I've given you a broad hint when I said more compile time programming. There is already a huge amount of C++ code that is undefined behavior free. It's already happened. It's not someday in the future. It's reality today. What is the keyword? Yell it out. Const expr. How much language UB can you have in const expr? Right. So const expr and const eval already reject. This is already true. We should be celebrating it. Undefined behavior. So remember that C++ interpreter that now runs inside your compiler? It actually will detect undefined behavior, language undefined behavior, such as signed overflow, some pointer arithmetic that's dangerous, division by 0. And many of those are also directly safety related. Here's that intersection. Here's an example. So the const expr factorial function, if you call the const expr factorial and then at the bottom you assign it to a const expr variable, so you're saying, really run at compile time. If you had called f of 1, that'd be just fine. F of 2, just fine. F of 4, just fine. But you know what factorials do, right? F of 13 doesn't fit into an int, and every single compiler diagnoses that today and rejects that code at compile time. That const expr code is UB safe today. That is proof positive that we can do that more broadly in the language, because we're already doing it in the C++ interpreter that's doing const expr. I'm not going to retake the poll, but I expect that there might be a few more hands this time in believing me that yes, in fact, we can eliminate the safety-related UB that's from the language because we're already doing it. So here are some more sessions that you can take a look at that are related to this work. And it doesn't fit on one screen, especially go to the Wednesday keynote by Amanda Rousseau of Microsoft, Embracing an Adversarial Mindset for C++ Security, because how we think about our code matters. That's going to be a great talk. Amanda is a wonderful speaker. You will love that talk. But take a look at all these talks. All of these topics are being delved into right here, this week, here at CppCon. So finally, let's see how both of these will help us simplify the way we use C++, the way we write C++ code, and also the way that we write C++ tools in the future. One of the questions I get a lot is like, man, the standard never wants to rip something out. We're always adding things to the standard. That makes the standard more complicated, right? Well, yes and no. And I give the operator spaceship example where we added a feature. It actually made the standard smaller because the core language feature was 12 pages, but it removed like 20, 30 pages from the standard library. So it actually simplified the code. But not every feature does that, right? You can't just keep adding random features to a language. It's going to increase complexity in a bad way if you just do that randomly. But if you do it intentionally and know what kind of features to look for, then the story is different. And the thing to look for is very simple. And you've probably heard me say this many times before, but to make this talk standalone, I'll say it again. Enable the programmer to directly express intent. When you add a feature like the range for loop, like a standard smart pointer so they don't have to make their own, like auto, like any other feature you can think of that lets the programmer express, like override, final, that say what I mean, they no longer have to say how to get that effect. They just say what they want and the language helps them. The standard library helps them. And so when we add features that directly express intent, one of the things that happens is we elevate what were coding patterns into much more concise and checkable and automatable expressions of what we want to do. We express what versus how. And we can use the intent already in the code to have fewer errors. So the code's not just simpler, which is like, yay, I got to write less code. I got to write more business logic, what I want, rather than the mechanics of how to do it, right? So not only is it more fun, I also have less debugging and less of a bug tail, because I just get fewer errors because I'm declaring what I want, and that helps the compiler, it helps the library, it helps the tools. So let's start by applying that to how reflection can help us. So in 2017, 7 years ago, at ACCU and then here at CppCon, I first started talking about metaclasses. And that metaclasses paper was virtually all, like 99% of the actual what we'd have to add to the standard, which wasn't specified in that paper, is reflection and generation. And the rest of the paper was just about when we have reflection and generation, here are all these things we can do with it. So A, as a carrot, like please give us this because look at all this cool stuff we can do that simplifies our code and makes it more robust. But also that it gives us a North Star, hopefully, to say, well, as we build this stuff, make sure that we're going to cover these use cases, please, right? So when I brought this for the first time to the Standards Committee in the summer 2017 Toronto meeting, in that room, there was a presentation by the reflection authors at the time, and then I came up and the first words out of my mouth were something like, hi, my name is Herb and I'm their customer. Because that's what metaclasses is about. It's about taking reflection and generation and saying, now what can we do with that? And so now I'm going to show you using the existing prototypes to do the stuff in my P707 paper. But the reason I brought, and that's the first major feature from what I later mentioned was CPP2 that I brought in front of the world, but it was as a delta to today's C++ syntax. And the reason I brought that feature forward first was, partly to fail fast, because the simplifications in CPP2, there were quite a few, but the two biggest areas that simplified, that were sources of simplification for C++ code were metaclasses and parameter passing. And metaclasses was the biggest risk because I thought it was great. I'd thought about it, it seemed like a good idea, but I had to validate several things. I had to validate that the committee would be willing to take this big step into running C++ code at compile time and doing reflection and generation and making that a first-class language feature. That was not guaranteed 7 years ago. I had to make sure by seeing your reactions in the room and on YouTube comments and in Reddit and in other places, is the community going to be willing to accept this idea, this direction? And then third, because we hadn't implemented all of it yet, if there's encouragement, then we actually need to go and find out and validate that it actually works. We think it does, we don't see the problems, but until you build it, you don't know that. And so that's why I presented that one first, because it carried the highest risk of all the CPP2 features. But we can write it now in the reflection prototypes for paper P2996, the one that was currently design approved on the language side for C++26. Here's an example of what you can do. So let's say I write my class widget. So I write my class widget, but I want to have different defaults. I want to generate some functions. For example, I might want to write a meta function that makes members, it makes it be an interface, is the example I'm going to show you, where all the member functions are public and pure virtual by default, and I generate a virtual destructor, right? That's what an abstract-based class interface is. Well, here's what I can actually write today in David's prototype, in the EDG prototype. I can write my class widget without those defaults, without the public and the virtual equals 0, and without the destructor. And then I can just stick that somewhere because I'm just going to use that as a template. Sorry, the word template is overused in C++. I'm going to use that as a prototype. There, I've got the right word on the screen already. And then I run this const-eval meta function, which reads the reflection of that and then generates the defaults and the extra functions that I want. I'm going to show you how this actually works today, and you can try it. And then meta classes, as described in my paper P707, is just this. I mean, it's going to be a half page. The rest of it is going to be like a half page proposal. Please let's make class paren metafunc paren, which is the syntax already approved by SG7 in the committee, that already directed that I use that syntax. Just make that mean the thing above. That's all. It's just syntactic sugar, but it's really important for usability, syntactic sugar, because it lets us do things like then get rid of the prototype so we're not carrying it around in the AST, things like that. So quick refresher example. Today I write class iFoo, public virtual equals 0, virtual equals 0. By the way, did you notice I just noticed the bug on the slide. What's the bug? I forgot the destructor. See, even I can't write this code correctly all the time today, right? So then we fixed our code. That was not intentional. I really try not to show bugs on slides. Anyway, if I wrote that, I wouldn't have that bug because I declare I want a class that's an interface and generate those things. So I get the right defaults, the right generated functions, and I can check constraints. Now that last part I can't do in today's prototypes that exist today. I'll call that out. But things like, there better not be any data members because interfaces shouldn't have data members, things like that. But here's the code. This code works today. There's a Godbolt link at the top, and this is just using David's prototype for the P2996 paper. Now, it does have generative extensions that go beyond P2996. So it goes several steps up that ladder, that step ladder I showed. But I can write this today in the prototype in the EDG compiler, where I do that pattern, namespace proto, and I write my class widget without those defaults, including without the destructor I forgot. And then I just say, in a const eval block, run the interface meta function, and all that is a const eval function, that's all it is, that takes a std meta info, a reflection. And then in the bottom half of the slide, you'll see now I can inherit from widget, and notice that I override functions f and g. That compiles, which means those must be virtual. But I didn't say virtual up there. In the source code, I set it on interface. Oh, interface. Well, of course you want public pure virtual by default. And this works. You can run this code today. And again, the only syntactic sugar I have left to propose is to allow this simple syntax for that pattern. But this works today. Now let's see what the code looks like. Here is that const eval function interface. It takes a reflection, and mostly I avoid all the namespaces, but I want you to see the namespace here, so I'm showing it. It's proposed to be std meta info, which is the current name. All of this is syntax that could change as it's being standardized. This is the current syntax. A std meta info, which represents a reflection of something in the C++ program. In this case, we expect it to be the reflection of a type. And it is. So the first thing I'm going to do is I'm going to call identifier of to be able to get the name of the type. In this case, it'll be widget. And then I'm going to start injecting code. This is the code generation part. Notice that everything in the box is just regular C++, but with some pasting, where I'm pasting the name as an ID. And the detailed syntax might change. In CppC2, you just paste it as a string and you don't have the separate ID and slash tokens and stuff. That's a detail. If I get the syntax with it's slightly ugly, but it does the work I want this feature yesterday. I care less about the syntax being beautiful. I want the functionality in the standard. But all of that is just code. And notice that the loop to generate the interface functions is another function. I'll show that on the next slide. This is composable. It's just code. We factor code. We might want to use that loop in some other meta function, so we make it a standalone meta function so it's reusable. And here it is. What it does is it says, for every member in the prototype class, if it's not a special member function, then go through and inject another virtual, pure virtual function that has the same return type, the same name, and the same parameters. So this works today, and it adds public and pure virtual, and you'll notice on the previous slide that we already added the virtual destructor here. So that is solved for us as well, just because we said interface. The one thing I'm not able yet to do is apply constraints and do error reporting. So I've shown the comment, and I'm assured that this will be coming. So I'll continue working with the reflection implementers and proposers to make sure that we get this. But I want to say else, if this is a variable, that actually compiles. The line that doesn't compile is print error, interfaces may not contain data members. So I can do that in CPP front today. I can't do it yet in the prototypes for C++26, hopefully reflection, but that's the only part that's missing so far. So meta classes, they're here. I'm able to implement them with this. And I'd like that little sugar too, because that'll make it that much more declarative. So here are the ones that are in the box with CPP front so far that I've written in my own syntax, my alternate syntax CPP2, which has more reflection already implemented, just to show what's possible. And this is all of the meta functions that were in my paper P707 I have now implemented, including struct, enum, flag enum, union, which are not separate type categories in CPP2 because they're just classes with certain constraints and generated functions. I wrote all of these except for regex. I'm going to talk for a second about regex because it is the biggest one yet written. I forgot to do the line count so I could tell it to you, but I think it's somewhere in like 2,000 to 4,000 lines of code. Somewhere in there. It's significant. I'll have to look up the exact number. It is a compile time regex using reflection and generation by Max Sagebaum. So to tee this up, the state of the art in C++ pretty much is Hanna Duzikova's CTRE, compile time regex. It is great. It does compile time parsing, compile time and runtime matching, and it's super efficient assembly. Blows std regex off the landscape, which is unfortunately not very hard. But she does a great job of it, and she blows other regex engines off the road too. Here's an example of what I mean by blowing off the road. Comparable with Rust, with the best regexes out there, but this is done in C++ with metaprogramming, but with metaprogramming that works today, which means angle brackets and const expr functions. So using a template engine as well as const expr functions. But it's a great and very important result. So what Max did is he said, well, let me try using CPP2 and CPP front and to do the same thing with reflection and code generation. And again, what he built, I just want to emphasize, even though it's in an alternate syntax, it compiles to full regular C++ today. Every regex you write that is compiled with his regex engine, you can call from any C++ code today on any compiler because it compiles to just ordinary C++. But what he did is instead of where Hanna was using a template stack, he used reflection and code generation. And here's how the code looks side by side. So on the right-hand side is the way to apply it, which is kind of like the class paren, regex paren syntax I just showed you, but in CPP2 I just used a slightly different syntax. It's mere syntax, it does the same work. And you just say, hey, here's a data member, which is the string value. Because I said it's a regex, the regex meta function reflects over the class, says, oh, I see you have a data member with a string value. Boy, that looks like a regular expression. Let me generate a huge engine for you at compile time for exactly that regex. That's going to be super efficient at compile time and runtime. So the sample runtime results for Max's implementation are comparable to CTRE. They're on the correct end of this graph. And that's runtime. The compile time results, again, still incomplete, are also competitive. But I want to point something out. So there's 3 sets of bars here. Well, and really I'm showing you can't see the third bar because the execution is just so fast. So we're going to mostly look at compile time here. The middle set of bars is the C++ compiler compile time. So Hanna's implementation, the blue one, has only the middle bar because there's no CPP front, there's no CPP2 code, it's full C++ today. And the left-hand bars, honest, there's a bar there. There's no bar for Hanna's implementation because she doesn't use that, but there is a bar there. If you squint, you'll see it. It's more like a line for all of the meta function and reflection and generation being done by Max's regex code in CPP front at compile time. I want to point out two things here. First of all, reflection and generation can be stinking fast. And we have proof by example. But once we do it, we could find to our surprise and delight that we actually get faster compile times. Now, this is a counterintuitive result, so let me hammer this point home, and I try to do this in every talk. Even today, when you take a template metaprogramming with angle brackets that uses the template system as a functional language, and you replace it with a const expr function, how many of you have done that and noticed that it compiles faster? It's like, but wait, it's running through a whole C++ interpreter? Yeah, but you said what you mean, and the compiler can love you back. You don't have to abuse this indirect angle bracket unless arrange templates in the right way and abuse the template system that was never designed for programming language computation and get a result back out as a side effect, as an artifact. That's just less efficient. It generates more heat, right? It's less efficient. So one takeaway here is just like writing a const expr function is faster than template metaprogramming nearly always with angle brackets. So reflection and generation can be faster because if we're replacing, it depends on what are we replacing, what is the net benefit. If we are taking template heavy code and replacing it with reflection and generation, which uses const expr, const eval functions, you should expect a performance increase because it's what we've already been used to. But how will this help us with not just the conciseness of our code, but also toolability? Well, today, I use the next few slides are all from my metaclass talk in CppCon 2017. So right here at this conference 7 years ago, when I first started talking about this, the examples are still the same. I just changed the syntax to class paren Q class. That's the main change here. Today, I have to write a Qt type with lots of extensions. And why? Because C++ today is not expressive enough to say all the things I need to be able to say to talk about Qt types. I can't talk about signals and slots and things like that in the language because the language doesn't know about those things, doesn't know about properties. However, if we could write the code on the right-hand side where we say we opt into writing, I'm writing not just any type, but I'm writing a Qt class, then when I say property, I know what that means. When the return type of something is or the type of a variable is a property, I know what to generate on the left hand, as if it was written by hand on the left-hand side. If a function returns the type signal, I know what that means, and I turn it into a signal, put it in the signal section. Slot, same thing. And this has three major benefits. First, it's easier to write the code. Second, it's easier to write the code correctly, because there's way fewer ways to go wrong. There's much more boilerplate on the left, which means there's more opportunities to misspell it. And we all will, right? But the third thing is it makes our tools, it can make our tools better. So today on the left-hand side is a rough block diagram of what the tool chain looks like when you compile that code with the Qt compiler. There's a separate compiler, the meta-object compiler. You write code in a mix of C++ and C++ with extensions. You run it through the meta compiler, you run it through the C++ compiler, you pull them all together, you generate, there's that word, generate C++ code. You pull it all together into the C++ compiler. And the reason we do this is because today, we can't get enough information, we can't say enough and get enough out of the C++ program. With reflection and generation, we will be able to do that. So I am not speaking for Qt, I am not making any product announcements for them, and we don't even have reflection in the standard yet. This is still a few years down the road, but hopefully we're talking a handful of years down the road. It's our near medium-term future. I know that the Qt folks are watching the reflection progress with this in mind. If we can deliver something that's powerful enough, folks like this will start adopting it. And that will mean simpler tools for us because then we can just use our C++ compiler. But it's not just Qt. The same thing happens where I work at Microsoft. COM has been around since the 1990s, and again, there's information that just doesn't fit in the C++ program, so I have to put it elsewhere, like in an interface definition language file, an IDLE file. And it's C++-ish, and it runs through a different compiler, and it can be either integrated into the C++ compiler, or it can be its own side middle compiler, but I have to do that complex tool chain today. If I could, with reflection and generation, simply say, oh, I'm writing a WinRT interface. Oh, well, then I know you need a UUID. You can make that a template parameter of RT interface. That works fine. Oh, you say property? Oh, I know how to generate a getter and setter, and I can generate the boilerplate for you. Generate multiple functions for that property. Have it decorated the right way. So again, easier to write the code because I'm declaring my intent. Then the compiler, in this case, the meta function author, can love me back. I'll make fewer mistakes because there's less boilerplate, fewer chances to go wrong, and I can get simpler tooling and just run this through a C++ compiler is my goal that I would love to see. Because you might have noticed that this mentions C++ CX. I think I've been saying this since my 2017 first talk about metaclasses. I led the design of C++ CX as well as C++ CLI. And I would love not to have to ever design such a set of language extensions again. I want C++ to be powerful enough. The only reason we did that was to avoid a separate tool, so we brought it in as language extensions, but it had to be an extension, a non-standard extension of C++. We only did it because we felt we had to have a separate tool, to avoid a separate tool, and because C++ didn't give us the information that we needed to express and to pull out. Reflection can give that. You'll notice that this should drive the requirements for reflection and generation and for const eval functions, because what am I going to want to do? I'm going to want to spit out the WinMD file that Windows needs. So I better be able to also do compile time I/O, text and binary, as well as spitting out the object files. But it's not just the big vendors. A lot of us have gone down this route. So here's an example from Benedikt Hegner and Axel Naumann of Yes, CERN. I was going to say CERN, and I thought, wait, no, CERT is the, oh no, but it's CERN, it's not CERT. Too many acronyms that are the same, of CERN. And what they do today on the left-hand side is they have a YAML script that runs through and generates 5 classes for every such YAML entity, 5 C++ classes. If instead we could implement that in the language with reflection, in C++ itself with reflection, get the types correct. Oh, that string, we know that's going to be a const expr string. Oh, that double, okay, fine. And we generate the 5 classes from this one class. Then we can take that left-hand tool chain and eliminate part of it and just use our C++ compiler, which simplifies our build. So all of these are examples I showed 7 years ago. I still view them as motivating examples, but we are now 7 years closer, and I'm pretty sure we're more than halfway there. So it's nice to see this stuff starting to come into the standard, possibly the first parts of it, as early as C++ 26. Now I asked Andre, who's got a bit of experience with reflection, for an example. Shall we ask him up so we can talk about it? In fact, would you mind if Andre and I sort of had a mini panel for the next 5 slides or so? All right, come on, Andre, let's come up. Now, I did not know that he'd be wearing all black, and it's just a coincidence that I'm wearing all black, but it's appropriate for stageheads because the first thing we're going to do is rearrange the stage.
This was rehearsed.
That part. Yeah, Andre's smarter because I tried to push this. Pull, you can lift. Anyway, so now I can see all of you. So Andre, here you came up with this example of an instrumented vector. So there's this const eval function, create instrumented type, and it returns a reflection. And then you say, using my vector equals splice this reflection. What's going on here?
So what's great about templates? They allow you to do designs with code that hasn't been written yet. And in the case of instrumented types, you get to reuse code that not only has not been written yet, but it was not designed to be hooked into, to be improved. In this case, I think the sort of the killer app for reflection is you get to create instrumented types. by which I mean take a type that was not designed to be instrumented in any way, and hook into it and modify it in such a way that allows you to, in this case, add the counter, counter for each call to a function, or time, how much time was spent inside this type's member functions, etc. So it's all about customizing code that not only has not been written yet, but has not been designed for customization.
So here, I notice in this particular implementation that we're showing, you're wrapping the type. In this case, it generates a std vector data member, right, and then you echo all the interface of it. That's right. The hard part today, right? Like anytime, when we create a wrapper, what's the hard part? Duplicating the interface. That's where, if you're me, half the time you start writing a wrapper by hand, and that's where you give up. It's like, oh, I got to write all those functions. Like, forget it. There's got to be a better way. Right. This can automate that, and in this case, you're duplicating the functions and creating another type. Yep. You could also, if we had reflection also on function definitions, which is one of those extensions that's coming later that we don't have initially, but we want to get, you could actually just generate a whole new type that doesn't just do the wrapping, but has all the original data members, all the original functions, including their bodies, and inject statements into them.
That's the shiny city on the hill. Yeah, that's where we want to go.
Okay. So would you be happy if you had a reflection and generation feature in C++ that could do this?
Yes, instrumented types are going to be the killer application of reflection. You get to instrument code that has not been designed to be instrumented.
Okay, I love that you, I'm gonna call you on that. I love that you said the killer application, because I know on the next slide is something that you're gonna say is also the killer application for reflection.
All right.
So.
Oh yeah.
We actually did rehearse this, but so Andre has also been involved with the D programming language. And so I asked, like, hey, what can we learn from reflection and generation in D? Because that's been a very useful thing there. And so he pointed me at this example, so I made a slide of it. It's a grammar where I'm giving the grammar as kind of EBNF, and then I can parse it at compile time. This is D code, so right. Void main is okay.
Right.
Want to tell us about this code and why it's important?
Well, first, I got to defend myself here. The killer application is because it enables also this.
Okay.
So, having that ability
it's the same
allows you, that's a natural consequence. But also it takes things quite a bit further. So as you folks see on this on the slide, we have this grammar represented as it's called PEG, parser expression grammar, which is a cousin of EBNF. And essentially, I have a grammar expressed in a very concise form and in a very simple meta language. And then you get to write a meta program that actually takes that grammar as a string and then output a full-blown parser for it. And I imagine where you can take this. The parser can be used during compilation and at runtime. So you can actually use that grammar for your own EDSL inside C++ and parse and use it during compilation. Or you can say, you know what, I'm going to parse some file during runtime, and you're going to define a more conventional parser. And now think of this. So this could be SQL, right? Could be regex, could be whatever DSL you want, but it could also be C++. And that is going to be a C++ complete application of reflection.
So you can tell why Andre wrote his 2001 book. If he sees something, he wants to see just how far can I push this thing, where little pebbles are falling off the edge of the cliff, but the whole thing is still on solid ground, right? It's like, well, how far can I go?
Herb, here's the funny thing. This whole reflection business is I told you so for David, for you, for me, because David has been at it for literally 21 years. His daughter from birth to drinking age.
Yes.
21 years.
2003 was the first paper.
Yeah, but he started before, right?
Okay.
So anyway, you've been at it for at least 10 years, right? So you've been at it with CPP front and all. I've been at it for 15 years or so. And I think we have now a crack team of yourself and David and Barry and Wyatt.
You're now a paper co-author. So this guy, you are going to be on the CPP, the committee fireside chat.
The fireside. Keep me by the fireside. Don't put me in the fire.
Because he's been around C++ for years and years and years and years. But you just attended your second standards meeting in June.
Yep.
So now you're officially a committee member, can't get out of it. And because of contributing, you're a co-author on some of the reflection proposals.
Yep. And I'm very happy with the team we have. I think David and myself and yourself and Barry and Wyatt and Dan Katz at Bloomberg and others. I think that it's a fantastic team. It's a great alignment of the minds here.
So some of you may at this point be thrilled, and some of you may be deeply terrified at, oh my goodness, am I going to have to deal with 100 domain-specific languages in C++? And this is where I'm going to channel Bjarne. I'm going to try to channel Bjarne, where he correctly says, yeah, fine, every new feature will get overused. And then we'll get over it. But this is one of the reasons why I say, and this leads to the next slide, welcome to C++ next decade. I personally am convinced that reflection and generation will dominate the next decade of C++, not only as we build it out, because C++ 26, if we're successful, will have just the first parts of it, just like ConstExpr, C++ 11 had just the first parts of it. And then we'll build more and more. But we'll also learn how to use it. And we'll do some overuse, and then we'll learn not to. Like if you've been doing C++ back in the 90s, you'll remember people did way too much operator overloading. Like, I'm not even going to mention the examples. They were terrible. And then we got over it. No, don't overload. OK, I'll say an example. No, don't overload operator pluses to say widget plus gadget and to add a GUI element to your window. No, don't. Operator plus is not intended for that. So it will get overused, but then we'll learn how to use it well. This is going to dominate what we do. It's no accident we have all these reflection talks even already at this conference. I personally don't think we're going to have a C++ conference for a decade where reflection isn't a major theme of multiple talks.
Yeah, but Herb, we got to talk about the elephant in the room. It's too big not to talk a bit about it. Just a few seconds. What's the big elephant in the room? What is the elephant in the room?
You love
AI generation.
No, he's right, compile time.
Compile time. That's not an elephant, that's kind of a moose. So the elephant in the room is AI generation. If you turn back for a second to the vector example, I actually, so this ChatGPT model cracked new Sunday, right, or Saturday, and it's called O1. And I used it, I told it generate a vector for me, and there's gonna be details about it in my talk on Wednesday, but essentially generated an instrumented vector for me, just the way I wanted, 470 lines of working code. And
ship it.
The influence of models for code generation, I think they're going to be a major, absolutely crushing topic for us. How does that influence language design, for one thing?
Well, in particular, I think this is a great example because here on the screen, we actually have two levels going on. We have the generated code, which is for this particular type. This is what you asked ChatGPT 01. Right. Yeah. It's like, for this particular type vector, give me a std vector that contains a type that has the same interface as std vector, wraps a std vector, and instruments the number of times that every function is called. It was something like that.
Right.
And it generated like 470 lines of code for you. It's great that it can do that today. I don't know if it's a year away or a decade away before it can write the create instrument to type function, even assuming that we have all of the reflection and generation. It'll be a while yet before it can write the generalized.
That'll be the next level.
Because that's a level of abstraction that requires currently human thinking. But maybe models can come to that if it's boilerplate. But here's the thing. The bottom part is definitely boilerplate. The create instrumented type, I'm not sure I'm convinced that that is boilerplate. And more meta functions on top of that are definitely creative. And that is where the line, I don't know whether there's a fundamental line, whether AI will ever cross the creativity line. Because they're definitely not creative today.
Nobody does.
But for boilerplate, they're getting awesomely good. So go to Andre's talk for more of that, but we need to keep going. So a requirements roadmap, what are we going to need? Well, for reflection, eventually, where we want to build it to is that any information visible in the source code must be reflectable, because I think you agree, if the programmer can know it, they'll want to use it. So sometimes people are used to say, well, do we really need to reflect attributes?
Oh, yeah.
Yes, oh yeah, because the programmer can see it and they will ask for it, and they did. Like, this is just totally predictable. But this also means defaults where there's meaningful white space to the programmer. And here's a great example that I like to use. Int func1 appears twice. It's the same declaration. In one case, it's private. In the second case, it's public. But in both cases, it has a default accessibility. That is, it appears before any access specifier. So with meta-class style, if I want to say, I write an interface class and I want to apply the default, so if you didn't write an access specifier, I'm going to add public for you. Now I need to know, not just is public, is protected, is private, I need to know is default accessibility. And so when I mentioned that to Dan, Dan actually added that to his Clang implementation for me. Thank you, Dan, so that I'd be able to write that code. But the one way to look at this that I encourage you to do is, notice the slight difference between this and this. View class instruct as just the first two meta functions that are baked into the language right now. Now it's going to be customizable where you can do that. But also, anything that can be written in source code must be generatable. You have a great example of that.
I don't like that word, by the way. Is it in the dictionary? Generatable?
I'll have to find a better word.
So, the simplest example is, you want to be able to create the identity function for types. Mm-hmm. That's the simplest case. And once you're able to do that, you decompose, you deconstruct everything there is in a type, and then you reassemble it back. It means you have complete control over the whole thing, right? Yeah. And that's a very cultural thing for our C++ programs, right?
Yes.
It's a very cultural thing. You should be able to
round trip.
Yeah, should be able to round trip and be able to look at every little piece and then reassemble it meaningfully. Once you have that, all of this is simple. All of the stuff is simple.
Yeah. So another part of the requirements slide, the second slide of the two, anytime that we generate source code, we're going to want to be able to see it because source code is our source of truth. So obviously the source code we wrote by hand, we can see, but even today, we get special member functions generated by the compiler that we can't see in the source code, but you still want to be able to step into the default copy constructor, right? Things like that. But we can kind of get away with it because it's limited right now. As soon as we have generation, there's going to be lots of generated code and we better be able to see it. And that's for debugging, like to be able to step into it, so to visualize it, to be able to have an IDE expand and collapse the post-meta function and pre-meta function version of the code so you can see what you're getting. So these are all tools that we can expect will need to be built over the next decade to make this usable.
Absolutely.
And in general, you already saw the example of WinMD files. We'll need to be able to do compile time IO to be able to spit things like WinMD files, and that's text and binary.
Yep.
So when you think of these examples like identity, it's important because I want to end this section with a risks slide because we're starting to get to where we're shipping the first parts of this, and that is great. But we can make mistakes, and what are some of the risks we want to be aware of? It's great to standardize some now and more later. That's great. But we have to have a North Star to know where we're going so that we're not standardizing a bit of this and then something over here that's disconnected, so it's piecemeal. We need to have an idea of where we're going, as we did with Const Expert. And the risk of bottom-up design, I took that phrase from something you said a few days ago, is that we may end up with overlapping features that don't fill the whole picture. I know that D has a great reflection and generation implementation. What could be better about it? If you had unlimited resources and a time machine.
Yeah, that's the thing, unlimited resources. We had very limited resources in D, so we were very opportunistic. Whenever we need a reflection feature, we would add it, and then we'd use it, and then we need the next one, and so forth. The problem is, when you go about things like that, it's easy to lose track of exactly what you want in the end. Like, what's your end goal here? And at this point, it's the borders of this power of doing reflection are fuzzy. It's unclear to anyone can D reflect on any class ever, and it's nobody knows. So it's possible that it's not, just because it has all of these bottom-up features that it's unclear whether they can be they're sufficient, right? So that's why I think it's good to have the end goal in sight. And it's very possible that also in C++, classes using a number of the very advanced features, like using reflection themselves, would not be entirely reflectable, and that's fine. But the only thing is you should know where the border is, right? Scala, by the way, Scala has similar problems, because in Scala it has a type system that is so expressive and so complex that nobody exactly knows where the boundaries are.
So I think there's a lot to be learned from experience we have in C# and Java reflection, in D, Lock3, CPP front, Circle, all sorts of other things. there are good things to learn from them. We can also learn the warning examples, things, well, what could be done better? And so one of the suggested aims I have at the bottom is in my paper, P707, the metaclasses I want to be able to write that particular use of reflection and generation, I would love those to be part of a North Star of like, let's try to make sure that we can implement that. And we're well on the way because I just tried and I showed you the code.
Awesome.
Andre's instrumented vector, and also to reflect and generate any type, possibly within the limits of whether it uses reflection itself, and also the preprocessor. We're usually excluding the preprocessor here. If we can reflect the preprocessor, somebody needs to write that paper, but we're not currently going that way. But we want to have that identity. I think that's a really good corpus of North Star to help mitigate the risks. So there still are risks, but we want to be clear-eyed about them and try to limit them by having these guardrails and having a destination in mind.
Awesome.
I love that you're a co-author of these papers now.
Thank you very much.
Welcome to the committee. All right, let's hear it for Andre. Thank you, Andre.
Thanks.
Let's put these back here. That probably violated some union rules, but you didn't see that, right? So now in the final section, let's talk about how safety contributes to simplicity of our tool chains, of our programs. Remember this slide from before, not only does programming language safety help software security and safety, but it just makes our programs more correct, more robust. We just make fewer mistakes, and that increases quality generally. Steve Klabnik, I think it was, wrote a really nice article, I think it was just this January, about how, correct me, sorry Steve if I'm misattributing it to the wrong person, about how Rust's emphasis on safety might have better been an emphasis on correctness and usability, because it's not just about safety. Programming language safety just helps you in many ways beyond security applications, just in your general coding, because you make fewer mistakes and you have a better velocity as a developer. So consider initialization again. I'll make I think it's a 1980s or 90s joke here. So is this righteous, most excellent code that the dudes would say, like this std array, which may or may not be initialized, and then we call a function to fill the array. If this code is uninitialized, is this righteous code? How many of you would say, yeah, this is righteous code, ship it? Nobody? Okay, well that's surprising. Oh, there are a few, okay, there are a few late risers, or I just noticed you. Okay, that's great. So yeah, there's a trade-off here. If A is uninitialized, this program is actually ideal, I'll say, except the static analyzer, and often a human, can't prove that fill of A fills A unless you go into the code. Unless it's a very well-known function like memcopy, in which case you've previously gone into the code, like you've looked at the implementation. On the other hand, if we just jam in zeros at line A, we're creating dummy values that we're then now immediately going to overwrite that we never use, but compilers are terrible at optimizing those away. And the first time you see this, you may say, well, that sounds like a lazy compiler writer. But they're terrible at it, despite heroic efforts, for the same reason. They can't prove that fill of A fills A. If they could eliminate those dead rights. And the usual plea is, but come on, optimizer writer, you're smart, you've got degrees, you've got experience, just nerd harder, right? And the usual answer from them is, fine, you teach the compiler to look through an opaque function call, oh, and by the way, to a function that hasn't been written yet. Good luck. If it's so easy, you go do it, right? I've had this conversation. I've been on the wrong side of this conversation. So force initialize a declaration and fill with pattern. So fill with pattern in C++26 is definitely better. And you can do that for things like just an int on the stack. But as soon as you start getting big objects and buffers on the stack, that's where the performance starts to hurt, those dead rights, that they actually matter. What we really want is initialize before use, so that most of the time, yeah, you initialize a declaration, but if you don't yet have a meaningful value, you just allocate space for the type on the stack, and then you construct it later, but still before its first use. And this is not rocket science, this is not invention. C# has this, Ada has this. Real programmers in mainstream languages are able to reason about their code and be successful with this. And so that's what I've implemented in CPP2, and that we can do also in C++. I'm going to propose the same for C++. All local variables of any type are uninitialized by default in CPP2. That's fast by default. You never have dead rights by default. You're guaranteed to initialize before first use on any branch path, which means you're always correct. You'll never use uninitialized. And it's also composable throughout parameters, which I'll give you a quick example. See my talk 2 years ago, 2022, CppCon, for much more detail, but I'll show you the summary slides from that talk, which gives us composable initialization. So here's the simple example. An int on the stack, A is of type int, it's just left to right syntax in CPP2, but this is still a C++ int A, semicolon. But it allocates space, but there's no initialization. The second line is commented out because it's actually rejected in CPP2. It's illegal. I cannot use A before it's initialized. And it wasn't because there's no equals something on the first line. Then I say A equals 5, and that is a true initialization. If this were a class type, that would be a constructor call at that point, and then I can use A just fine. And this works for any type, not just int on the stack, but it's the same rules for every type. Vector of strings, anything, big buffers on the stack, anything you want. So here are just some quick screenshots to illustrate this. I encourage you to look at my 2022 talk from 2 years ago at this conference, where I live demoed these in detail on stage. I think it was this very stage in this room, if I remember right. So main goes through and creates a pointer on the stack. P is a pointer to stood string. I initialize it in the if, but not on the implicit else branch, and that's what the error message says. Error, if initializes P on the branch starting at line 8, but not on the implicit else branch, program violates initialization safety guarantee. You can't use before initialize. Here's another example where I have X is a stood string on the stack, uninitialized, so I've only allocated space, no constructor has been called. So if flip a coin is true, then I assign the value X, Y, Z, Z, Y. That is a constructor call in CPP2, because it's the first use, it's the definite first use of X. It was uninitialized, and so this constructs X. Else, I call this fill function, which, long story short, uses an out parameter, which in its body will know to do a constructor call. It knows whether it gets an initialized or an uninitialized argument, and it will do a real constructor call. So really, any function with an out parameter is effectively a delegating constructor. It's generalized in CPP2. We can do any or all of these same rules in C++. Finally, bound safety. Remember, that's the low-hanging fruit. What I've already implemented, and again, I'm going to propose that we consider this for C++ in the bound safety profile that Bjarne is promoting, Bjarne and Gabby. What I've implemented is every subscript expression A sub B, if A is a contiguous container, so it has stood size and is contiguous, and B is an integral type, we inject a bounds check at the call site. And this is integrated with contract handling in CPP2, so if you violate it, you get a bound safety violation. That's customizable, so it fails fast by default, but you can customize it to do whatever you want, including log and continue or do whatever's appropriate. One of the cool things about this is I hoped it would just work. It does just work. This gives me bound checking for every standard library implementation. This works on GCCs, on libc, std C++, on libc++, on MSSTL, without any change to the standard library. It means some code can say they want bounds checking and not, and still have an ABI compatible type, because I didn't have to do anything to the standard library type. It works for std array, std vector, the std ranges views, anything that has std size and is contiguous. It also works for C arrays because those have std size in C++. And it also works for third-party containers, Qt containers, and other containers that aren't part of the standard. As long as they follow the std size customization, it just picks it up and works. If std size is available, We just inject the bounds check. And I didn't have to go and update anybody's libraries. They just work. No ABI incompatibility, no worrying about link compatibility. And so I would like to propose this, and we'll see what the committee thinks. The committee is wise. They will find bugs if there are bugs. But I would love to see a future C++ where if you enable the bounds profile and recompile, that by default, all of your subscript operations are just safe. They're just automatically bounds checked. And of course, we can always opt out if we need to for performance in an inner loop or something like that. The knife is still there. It's just in a drawer by default. So here's an example that actually works, and I've shown this, and I'll show you the exact output. Those first two lines are ordinary C++. Uncomment either one of them, the array or the std vector. And then that third line, if you compile that today in CPP2, and I hope in the future in C++ with the bounds profile enabled, anything wrong with that line? It's actually line 7 in my source code, which you'll see in the error messages. Anything wrong with that line? I've got a container of 1, 2, 3. I print 1, 2, 3. Yeah, how many of you have made that mistake at least once in the last month? Okay, a few hands. Ever? All. Right. I made this mistake while making the example. So this CPP2's range checking, bounds checking, caught this mistake in my own example. What I did in that case is I had a 1, 2, 3, and I had simplified it down to 2, but I'd forgotten to make the loop one less iteration, and it caught it. I love living in this world. I really do, and still have C++. So here's what happens today. If you compile this code with CPP front, if that third line is in a CPP2 main line or function, it will print 2, then it will print 3, and then it will print and give you exact source, file, and line number and function attribution if the C++20 source info header is available. Say bound safety violation, out of bounds access, attempt to access at index 3, min-max is 0.2. And that's not just because Microsoft is smart, it works in GCC 14 as well, and in Clang. I see no reason why we couldn't decide to do this in the standard, and so I'm going to propose that, and we'll see where it goes. But again, what are the risks? It is good to provide safety guarantees. It is good to provide features. We have to know they work. We have to know that they work well together. We don't want to do ad hoc safety design. We want to take known good things, shift left to compile time. We want to make existing code correct by construction, or just inject checks where necessary at runtime to do the right thing so that we can help as much existing code as possible with no manual code changes. Just recompile with a C++ 26, 29 compiler, and it's just better. It's just safer. That is going to deliver the most value to the many billions, who knows how many lines of C++ there are out there, as we're able to recompile it and harden our software against intrusions, against disclosures, against accidental life safety issues, and just our own usability as programmers. So that's a theme I'd like us to think about going forward. As we add things to the language, be intentional. What things can we add that enable the programmer to directly express their intent, or take the intent they already expressed and make it safe, like with those subscripts? Bjarne is right that inside C++ is a smaller, cleaner language struggling to get out, and we can make even the big language safer and easier to use in many of these ways. C++26 is already doing it, which is great to see. And like he says at the bottom, most of the simplification will come from generalization. So we've talked about reflection and how that's getting real. It's getting to where the first parts of it look like they will be landing in the standard that is going to be feature frozen a mere 9 months from now. Safety improvements have already been voted into C++26 that make uninitialized local variables no longer undefined behavior in a C++26 compilation. And both of those things are going to help our simplicity going forward by directly expressing our intent so that our code is simpler, our tool chains are simpler, fewer side compilers, fewer annotation languages, because we can express it in C++, because we've grown C++ to be powerful enough to concisely express our intent. And that will give us a platform to build on. So a lot of this is already happening. C++26 is exciting for not just those two reasons, but those are the two big ones that I have focused on in this talk. So as we peer forward, I think these will dominate C++'s next decade. And it's exciting times to be doing C++. It is exciting to, after the legitimate complaining, to see safety improvements landing and becoming real. It is great after many years of working on reflection to see it becoming real, because it's going to be dominating. It's probably the most impactful feature we will have ever shipped in the standard, by far. And it'll be as game-changing as C++11 was, and we'll be absorbing it for the next decade to come, as it makes our code simpler, more effective, and it makes things that are hard to write today easy, and things that are infeasible to write today possible. We are a powerful library building language, and we're about to see another surge in that. So it's exciting times. Go to the other talks in this conference where you're going to hear much more about both of those things, and enjoy the rest of the conference. But one last thing. Before you enjoy the rest of the conference, as soon as this talk ends, instead of sitting around listening to the band, which we would normally do after every keynote, go out there and get your picture taken. Everybody ready? Let's go. Thank you all. Enjoy the conference.